In the regression analysis, we're concerned about the stronger relationship between two variables. So when we looked at the R, it was just telling us strength and direction. What it didn't give us was a stronger amount of correlation between X and Y. Certainly, sales calls made and copiers sold is related. But what if there was a way to know with a greater degree of accuracy, if I make one call, this is what I predict as the amount of copiers sold. Again, if I make one call, what is the amount that I predict will be the number of copiers sold? So that is where regression analysis comes into play, a stronger test for the correlation between two variables. So keep in mind that regression analysis measures the relationship between variables, just like an R. However, now we're going to bring into the conversation the concept of the slope, right? So that B or beta, which it will be called later, is our slope. And slope is no different than what it meant back when you were taking, you know, your linear algebra or your college algebra types of courses. Slope is still going to tell us something about the change in Y over the change in X, right? And X is going to be your driver. So as X goes up 1, right, how much does Y change? Does it change by 0.3 positively? Great. If so, because then you know consistently that as my X goes up by 1, that I'm going to have a positive change of 0.3 of my Y. So rise over run, change in X over change in Y, or change in Y over change in X, those things still apply if we're talking about the slope. So formally, the relationship between X and Y is defined by the values of the intercept, okay, and the slope. In regression analysis, we use the data to estimate the values of A and B. Okay. Assuming a linear relationship between the size of a home and the cost to heat would be one way to look at regression analysis, and you can see the other example there. We call the Y the dependent variable. Look at the setup here. And by the way, this setup is no different than your standard setup of Y equals MX plus B, right? If you recall from your college algebra days, Y equaling MX plus B is the formula for a linear curve, okay? There's no difference here when we look at this setup. We're just changing the names of letters. So Y stays Y, right? The B right here, this Y-intercept, right, is now becoming the B. We're calling the A the B. I know it's a little confusing. Or I should say we're calling the B the A if we're looking at regression analysis. The X stays the same. All right, and then this M, which was your slope when you were taking college algebra, now is going to be known as B, okay? So the formula is the same, it's just that we are changing the names of the letters. All right. Keep in mind, it's very important to remember that Y is the dependent variable. Y depends on how X changes, okay? X is independent. It does not change based on what happens to Y. Y changes based on the movement of X. Okay? X is the predictor variable, meaning as X goes up by 1, it's going to predict something about Y. Okay? If we were replacing these variables with actual words, right, we could say there is a relationship between heating cost and home size. And home size determines how much your heating costs are. So home size would be your X variable, and heating cost would be Y, okay? Because X is determining Y. If said differently, Y depends on X. That's why we call Y, right, the dependent variable, because Y depends on how X moves. And X is your predictor variable because X is going to predict how much Y moves or changes. Okay, so understanding that is a critical piece of understanding regression analysis. Okay, car weight in miles per gallon, same logic applies. So whatever you're putting as your X, keep in mind, you are telling yourself in the world that this variable will determine or predict what happens with this variable. In the setup for change in Y, right, Greek letter delta, change in X, the one that moves first is always your denominator, right, as that changes by 1. Then something happens, right, to the Y. So your X is going to determine or predict what happens to Y. Can't say that enough. So the regression analysis estimates A and B by fitting a line to the observed data. Okay. If we have, again, copier sold and sales calls made, as we do right here, what we're saying is that there's a strong relationship. We know that the R is 0.865. That's fine. But then we can ask ourselves, going a step further, what if we put a line in this data which represents the shortest distance between the line and all the data points? Okay? The shortest distance between the line and all the data points. By definition, if that's what we're trying to do, then the line must be within the data, something like I have listed here, right? Because that's a shorter distance, that's a short distance, that's a short distance, that's a short distance. If I put the line way out here, then we have not minimized the distance, right? We have not minimized the distance between the lines and each data point. We want to minimize that distance. We want to put the best fitting line into the data. Why would we want to do this? Because if we can put the best fitting line, right, which is this one, into the data, then we could use that line to predict a stronger relationship between X and Y. That's exactly why. If we put a line that best fits the data, okay, the one I've listed with the arrow here, this one here, right? If we put that line in there, then we can say, well, if I know, right, this relationship based on the slope of this line, then I can use X to predict Y. Okay, that's why we want to put a line in there. Will it always be right? Will it always be the case that, whatever, X is, Y will be in terms of the change? No, not always, of course, because these dots are not directly on the line. But if I put a line of best fit in there, then I can comfortably predict without being too far off. Okay, so that's why we call it the line of best fit. It's not going to be a line that's up here, that's down there. It's going to be a line that shortens the distance between the data points and the line itself. Why? Because we want that line to be used as a predictive tool for when X changes, how does Y change? Because this corresponds to that straight line. But we have to get the straight line first. We've got to get the best fitting line first. It's called the least squares principle. Determining a regression equation. Okay, what's the equation? Right? This is the equation. By minimizing the sum of the squares of the vertical distances, right? The vertical distances. This is a vertical distance. This is a vertical distance between the actual Y values. Remember, each dot is a Y value and the predicted values of Y. And what I mean is each dot here, okay, is an actual Y value. We got the dots because we had the Y's in the X relationship. The predicted Y is going to be the Y's that exist on the line of best fit, right? A line is nothing more than a connection of dots on a graph. That's really what a line is. It's a connection of dots. And so all of these dots that exist that I just put on a line are predicted values of Y. Predicted because as X changes, here's what I predict Y to be. And again, if we can minimize the distance between the actual and the predicted, we have then created a line of best fit. So the regression analysis starts with asking the question, what is the expected number of copiers sold by a representative who made 20 sales calls? Okay. right now, well, there's a few keywords. There's a few keywords. Expected means you're predicting. Okay. By a representative means that we're looking at the sales call side. Okay, we're looking at the X variable. And 20 calls is the number that corresponds to the particular X value we're concerned with. So if we drop a 20 in here, what will Y be? Right? That's the question that's really being asked here. If we drop a 20 in there, what will Y be? If we drop any number in there, right? Any number, 21, 121, what will Y be? The reason why we're able to ask this question now, it's because we're going to create this regression equation. And once you create this regression equation, which comes from the data, you can then put any X in there. You can ask any question, 1,000, and you'll have a predicted Y. Okay, because then it's just math at that point. Let's figure out what our B is, and let's figure out what our A is, so that then we can create a predictive equation. Okay, that's the goal. Descriptive stats, if you wanted to find the R, again, you can run descriptive stats, and hopefully you've already watched that video from my business stats, the business stats area of the website, and you would have come up with your means, and you would have come up with your standard deviations, right? Here's your means, here's your standard Ds. Okay, so you'd be done with that. If you do that, 0.865, or you just run the Corel and you're done. Number one, find the slope B of the line. Okay, this is the formal equation for finding the slope. If you already found your SY, and you've already found your SX, and you've already found your R, which you would have if you had done it by hand, right? Here's what your beta would be, okay, or your B. And B is still interpreted the same way. It's saying that if there is a change in Y over a change in X, then as this goes up by 1, then this goes up by 0.26. Okay, so as sales calls goes up by 1, then the copier sold goes up by 0.26. So that would be the formal relationship if we're finding the B, which eventually will be the B we use to fit into our regression equation. What do I mean? That's what I mean right there. Okay. So the interpretation of 0.26 is what it always has been. As X goes up by 1, Y goes up by 0.26. Okay. And I know it goes up and up because this is a positive, right? It's a positive. So I know that as one goes up by some direction, the other one must go up by the same direction. If we wanted to change this but keep it positive, right, we could say as this goes down by 1, right, your Y goes down by 0.26. That is also a positive relationship, okay, because both of them are going in the same direction. So either way. All right, so we have found our beta, right, using kind of the hand method, not Excel necessarily, and that's fine for now. Finding the y-intercept, here's our formula, right, y bar minus b times x bar. And if you plug in the numbers, right, here they are, and then you'd have 19.96, okay, which is found right there. And of course, 19.96 as your y-intercept represents the fact that if this were 0, right, if x equals 0, you still would have 19.96 copiers sold. In other words, if no one made a sales call that month, which is the period we're looking at, then you'd still have y equals 19.96 copiers sold. So the y-intercept represents the ability to understand that fact. Okay, set this to 0, set x to 0, you still have something sold in terms of copiers. And of course, if we were to graph that, okay, this is y, let me make that a little bit better. If we were to graph that, and that's y, and that's x, we could say our y-intercept is 19.96, and it's a positive line, so it would look something like that. Okay, there's your 19.96. So even if y, or even if x is 0, you still have some y being sold. All right, so with that information, we can then create the regression equation. We just take this number, plug it in right there, and we take this number, plug it in right there, and ultimately we're done. We've created the regression equation. Okay, the predicted number of sales, step 4, if someone makes 20 sales calls, then can be replaced. So the number of sales calls is replaced by 20, and then you just do some math, right? You do some math. So if we take 20 times 0.26, we'll get a number. If we add that number to 19.96, we will get 25.1792, which represents how many copiers are going to be sold if somebody makes 20, or if there are 20 sales calls made. If you say instead of 20, right, 30, then just replace that with 30, right? And of course, then you'll get a new Y. If you want to go 3,000, right, just replace it, and again, you'll get a new Y. Okay? So the point of creating the regression equation is to allow us to predict a Y with any given X. With any given X. Questions on that? I will go to Excel next to show you the Excel technique. Questions on that?
So the 45 is what on that example?
45. Oh, 45 is the Y bar. 45 is the Y bar. So we are talking about, let me get this up here. Yeah, so 45 is your Y bar. And that comes from this right here.
Okay.
Okay. So just finding the mean using your descriptive stats for Y bar, for Y.